Okay, the last specific kind of statistical procedure I want to talk about in the course is called analysis of covariance. ANCOVA. Yet again, is a bit of a twist on our simple analysis or one-way analysis of variance, and we've done all kinds of things with analysis of variance and changed it around a good bit. This is analysis of covariance. And here's where analysis of covariance might come into play. Let me give you a scenario. I have two classrooms, Mrs. Johnson and Mrs. Brown classroom. And Mrs. Johnson and Mrs. Brown, they teach differently, so I want to know something in terms of what kind of test scores come out of there. I'm not advocating test scores as sole evaluation of teachers, even though that's a lot of what we do. But let's say we're going to compare test scores from those two classrooms. Now, what I cannot do is what a true experiment is. A true experiment would be if I had, let's say, 60 children, 60 students, and I randomly assigned those 60 students to one of the two groups. So I had 30 randomly assigned for one category or one classroom, and I had 30 randomly assigned for the other classroom. You can't do that. Classrooms are already intact. If you do it once the beginning of the year, maybe so, but as the year goes on, even if you randomly assign them initially, different experiences make for differences between the classes. So the problem I'm going to run into, or I'll likely run into, is that, okay, I want to look at some kind of test scores on the end, but maybe the students are different to begin with. Doesn't it stand to reason, gee, common sense really does come into play sometimes, doesn't it stand to reason that if a class has higher achievers on the front end, that may affect them in terms of what they score on the back end after the test that you're going to compare? So is it the difference in teachers or difference in instruction, or just does the difference at the end come about as a difference because it was initially there to begin with? And I don't know. Now, we've talked a little bit about how to deal with those kind of things, but it's not always a very good idea. You'll remember we've done several examples where we use gain scores. We just take the post-test and subtract the pre-test from it and see how much improvement they made. That's okay if everybody's kind of, or overall, on average, they're kind of near the middle, but what if they're not? What if one group is or even individuals are higher or lower achieving, significantly higher, significantly low? In that case, gain scores are a problem because if you've got a bunch of higher achievers, you only have so much to gain. So it's not as likely that you're going to have so many points earned in terms of gain scores than if you start out low. So the problem with gain scores is when you have some extreme scores to begin with. So the question we have to answer, well, okay, but the two classes are different to begin with. How can we make a comparison on the test I'm going to give them? Again, I use test as not a model example, but just one that we do all the time. There is a procedure that makes some adjustment for initial differences if they're not too far out of whack. And by out of whack, I mean if those differences aren't too extreme. If one class is way high and the other class is way low, this particular procedure probably cannot make that much of an adjustment. So that procedure is the analysis of covariance process procedure, ANCOVA, analysis of covariance. And again, what analysis of covariance does, it allows you to compare outcomes and make some adjustment for initial differences. And what that initial difference is, let's say those are pretest scores, those initial differences, that's called a covariant. We're going to have room for a covariant when we're going to be lazy and make SPSS work out all this stuff. So ANCOVA, analysis of covariance, compares two or more groups and makes some adjustment for initial difference. And I'm sure you're all thinking, well, how do you know if the initial differences are not too far to adjust for? And that's part of the process. So, if you will call up Green and Salkin, and we're in lesson 27. And we're going to look at data file 1. Let me see if I can punch the right button to get this on the screen for you. Okay, I don't want to jinx it, but it's working so far. So let's read the scenario. That's the bottom of page 209. And this is a takeoff of our vitamin C example that it's a little bit of a twist on that. So again, we want to see whether vitamin C seems to be an effective treatment of colds. I've got 3 groups. Groups that receive a placebo, groups that receive a low dose of vitamin C, and groups that receive a high dose of vitamin C. And you can see from my first column here, I'm identifying whether the individuals are from group 1, 2, or 3. And we've programmed this in already to tell that I'm going over to variable view to where if they're getting a placebo, they're coded 1, low dose they're coded 2, high dose they're coded 3. So when we get an output, it'll label it this way for us, so we don't have to remember what 1, 2, and 3 is. So that's the first one. The second column, the second variable is pre-days. And the third column, the third variable is days. So days, this is days of sickness or days of discomfort now. So lower days of discomfort means you're feeling better, you're more well. So person number one, person number one didn't get any vitamin C at all. That's group 1. He wasn't sick at all last year. He was sick 12 days this year. So no treatment, and he was sick more. The next person, person number 2, also no vitamin C. He was sick 10 days last year. He's sick 8 days this year. Let's go down and pick out case number 11. The person got a low dose of vitamin C, for example, was sick 14 days last year, was sick 12 days this year. And I'll go down and pick out one of number 3. Case number 21, got a bunch of vitamin C, wasn't sick at all last year, but he was sick 6 days this year. So there's a lot of variability within the groups in terms of how many days they are sick, whether they take vitamin C or not, and how much they take of it. Okay, so our independent variable is the group. Which group you're in. No vitamin C, a little bit of vitamin C, a lot of vitamin C. The dependent variable is the days of this year. How many days you were sick or how many days you experienced discomfort this year. But if I look at these groups and how sick they were last year, there may be some differences in terms of how sick they were last year. Doesn't stand to reason if you were more sick last year, you're going to be more sick this year, and vice versa. So we don't know. So analysis of covariance may adjust for whatever differences there might be. So the first thing we have to do is we have to see if, and here's the technical term for it, we have to see if these differences are too far out of whack to make the adjustment. If they're too far out of whack, we can't do an analysis of covariance. So I'm going to, and there my stuff disappeared again without touching anything. See anything yet? I don't think you do. Nope. Okay. I shouldn't have said it was working. All right, let me try it again. Try something a little different. Okay, you have both going and nothing's working on either one of them. Yeah, my screen says that too. Okay. All right, I'm going to do this. I'm going to close this one out. I'm going to open up, or close something out. I'm going to open up another one. No luck. No luck. Okay. Oh, it's back. I'm not showing on the what I'm using to monitor. Not now. Okay, great. Okay, let's try something different here. Now it's back, right? There it is. Okay, yay. All right. All right, so recapping what I think I just said is the group is the independent variable. The dependent variable is the third column days. Those are days sick this year. And the covariant, the whatever initial differences there might be between the groups, is based on number of days sick last year. So I'm going to go to, no surprises so far, analyze general linear model. Again, we can go to that place for all the types of ANOVAs. And now we're univariate again because we have only one dependent variable. And that's how sick you've been this year. So I'm going to go to univariate. So the treatment group is the fixed factor. Again, that's synonymous for independent variable. And it's a little bit longer than probably what you're seeing label-wise, but if you, the dependent variable is, I think I got that one right. Let's see the other one. Yeah. Days with cold post days, that means after the treatment. My covariance, you probably have, I don't know, you may have noticed this covariant box before. So it's been here. We just haven't done anything with it. We're going to do something with it now. So my days of sickness from last year, that's the covariant. That's what accounts for whatever differences there may be that already exist before I'm measuring days sick this year. Now, a two-step process, or maybe a two-step process. Again, it's kind of like the old, do you know what time it is? If the answer is yes, there's a second step. So the first step's a lot like that, do you know what time it is step. If I go, okay, I've got everything in place there. I'm going to go first of all to options. Nothing new here. I'm going to move the group over. And I'm going to select descriptive effects, estimates of effect size, and homogeneity testing. And it's going to matter here. Here's where this finally comes into play. We'll see in just a minute. I bet you can't wait. The homogeneity test. So good for that. So I'm going to continue from there. And by the way, since this is a univariate, not multivariate test, I'm going to leave my significance level at 0.05 because I have only one dependent variable. So I don't have to fool with that. So we continue from there. We go to Model, and I want to choose Custom. And when I choose Custom, a couple options highlight for me. And those things on the left box, I want to move both of those over. So you can click on one, move it over. Click on the other, move it over, or double click on it. But I also want to do this. I want to highlight one and shift so they're both highlighted and move them both over together. And you see it says group by pre-days. That's the kind of thing we've seen before in our last procedure. I don't know why it couldn't just give that to us here, but it can't. So move one over, move the other over, then move both of them over. Group by pre-days. The default drop-down option here in the middle is interaction. And we'll remember that, we talked about finding interaction with two-way ANOVAs, the same kind of interaction here because we've got these two variables. And I'm going to click Continue. And I'm going to click OK, and I'm going to get an output window. I'm going to scroll down and I'm looking for one particular line, and that particular line is the one, and again, this is similar to another procedure. That particular line I'm looking for is the one that says group and pre-days together. Now from that line, I can write this. With the numbers on that line, I can write F of 2 and 24. The F value is equal to 1.417. I'm sorry, 1.474. And the p-value significance is equal to 0.249. And by the way, one other thing I'm going to report, I've got my partial eta squared, of course. I'm going to report the mean square. Because you'll see that comes up in the write-up in just a minute. And that is something I covered up here. Again, we're almost always looking for the last number in a column. So the mean square is 11.884. Now the key thing is the significance. Now remember what we were doing. This is called our test of homogeneity, or the homogeneity of slopes assumption. This has to do with whether things are too far out of whack or too different to make an adjustment for. So that difference has a significance of 0.249. That's not a significant difference. So therefore, the initial condition is not too far out of whack to adjust for. Therefore, we can run an analysis of covariance. So let me say that again in shorter language and maybe not so wordy. For the first step, the homogeneity test, I'm looking to get a level that's not significant. I'm circling that on the screen. If I get that, then I can continue. If I don't get this, if I get like a 0.002 or something, I can't do an analysis of covariance. That means it's too far different to adjust for. It's too far out of whack. This is not too far out of whack. So the difference is not significant enough that we cannot adjust for it. We can adjust for it. So kind of a new first step. That's the biggest thing in this analysis. So we've determined then that we can run an analysis of covariance or an Ancova. So fortunately or unfortunately, we're not finished. So to run the procedure, and I'm going through the steps, what I've done so far is I've gone through the steps on page 214. And that is headed as conducting a test of the homogeneity of slopes assumption. You probably use that phrasing in your everyday conversation, I'm sure. But what that means is just a test to see if we really can do an Ancova. And we can, because the number right here is not below 0.05. So we can run the test. Now, the good news, some of the good news, though you'd think there'd be some in there somewhere, some of the good news is that things that we need in place, we've already put there. That's why we made some of the choices we did a little bit ago. So to actually run the test, and I'm going to leave my output window open because this is part of what gets written up. I'm going to go to Analyze, going to go to General Linear Model, going to go to Univariate, and when I select that, I'm going to see the boxes that are already have variables in the right places. Voila. And to run the test, I got to go back and undo a couple of things. So remember, we went to Model, and we flipped that over to Custom. Go back to full factorial. That was the default value. And again, this is outlined on page 215, the step 1, step 2, step 3, literally. So go back to full factorial, tell it OK, then go back to options. Model and options were the two places we went. And I don't think it makes any difference which you go to first. Go back to options. And the only thing we want to do here is we want to click compare main effects. Remember the main effects. Remember we talked about that in the two-way ANOVA or the multivariate ANOVA. So I'm going to compare main effects. And then when I hit continue, it's going to take me back to my previous screen. And now when I click OK, that's going to give me an output window. So what we've done so far, we've said we could run the Ancova, and as soon as I click OK, that will tell us what the results are, and there it is. So if I scroll down to the test of between subject, and I look at the same two lines I'm used to looking at, and that is the groups and error lines, those rows, I'm going to see information from there that I can write f of 2 and 26 degrees of freedom, because those are under the DF column, 2 and 26. That f value is 6.45. The p-value is equal to 0.005. That is significant because it's less than 0.05. That means I've got, at this point I'm looking at this like it's a plain old ANOVA. You would see numbers a little different than if you ran it as an ANOVA without the covariate, but again, it's making that adjustment. So I've got some significance somewhere. Something is significant from something. I don't know what yet because I haven't scrolled down and looked at it. But because of this, I've got to look at specifically where those differences might be. So I've reported the significance level or the p-value. I'm also going to report partial eta squared. And again, remember, I'm going to report mean square, which I'll come back to that in a minute. So now if we scroll down, finally, last thing we need to look at is the pairwise comparison. We've seen this kind of thing before. I'm going to compare placebo to low dose, placebo to high dose, and low dose to high dose. Anything I've not connected or just duplicate information. So I'm going to look at those three lines. So if I look at the significance value for those three lines, this is less than 0.05. This is less than 0.05. This is not less than 0.05. So having conducted the analysis of covariance, because we made that adjustment for the initial differences, I can say that, it looks like the placebo is significantly different than both the low and the high dose. But the low and the high dose aren't significantly different from each other. So here's where I put my check marks on where the two differences are, and those are two lines both comparing amounts of vitamin C with no vitamin C, which is very similar to the result. Actually, it's the same result we got the last time we did this as just a plain old ANOVA. I'm not sure if they were using the same numbers or not. I don't think we were. The thing to say, the placebo is significantly different from both the low and the high doses. That's the easy shortcut way to say that. Out of three possible pairs, two of them are significantly different. Placebo in low and placebo in high. So it's placebo that's different from both the other two. Other questions, observations, anything from anybody? Do we want to report eta squared at the end of the, yes. Yeah, and I'll show you in the write-up in just a minute, I'll show you where that goes. where we'll walk through the write-up and I'll point out where he goes. Good question. Anything else at this point? Because what I want to do next, I want to look at the write-up that's provided in the textbook and just go through and point out where all the numbers come from. Anything else before we do that? We okay? Or at least okay that you can watch this video 28 times because it's so entertaining and fun and good stuff? All right. So let's look at, I'm just going to have to erase, I wish I could show all this at once, but I can't. So there. All right, the APA write-up is provided for you for this particular set of data and this analysis on page 220. Now, your chapter also, your lesson also deals with what happens if you don't pass the homogeneity of slopes test. I'm just not going to worry about it. Because we're going to see what happens if you can when you can run the Ancova. So if you can't run an Ancova, you just have to run something else, play a plane on the Nova or whatever. But walk with me through page 220 where it says under results assuming homogeneity of slopes. That means you could run the ANOVA or the Ancova. So again, I will insult your intelligence by reading with you and stopping when it gives us numbers and what they mean and showing you where they come from. And it's basically all the stuff I've circled. A one-way analysis of covariance. One way means you have one independent variable and it's not multivariate, it's just univariate because there's only one dependent variable. Anyway, so a one-way analysis of covariance and Ancova was conducted. The independent variable, vitamin C, included 3 levels. So you describe the independent variable. The dependent variable was the number of days of coal symptoms during the treatment, and so that's the dependent variable. And you tell what the covariate is. The covariate is the part that might be different to begin with. In this case, the covariate was the number of days of cold symptoms before treatment. And that's what we put in. Those are the things that we put in the respective boxes. A preliminary analysis of evaluating the homogeneity of slopes assumption indicated that the relationship between the covariate and the dependent variable, you can use those exact words, did not differ significantly as a function. That came from this line right here. Well, stop. Group by pre-days. And if you look at that line and you, with one eye and with the other eye, if you look at what I'm about to read on page 220, f of 2 and 24, here's the 2, here's the 24, equal 1.47. That's this number rounded off. The mean squares, that's called MSE. They use it to abbreviate MSE. 11.88. Here's my 11.88. Again, the last number in the column, almost always. P-value is 0.25. They rounded off that 0.249 to 2 points. So you can, again, you can round it to 2, or you can use the p-value to 3 if you like. And the partial eta squared is 0.11. That comes from the 0.109 rounded off to 0.11. So that's where they get that first set of numbers, right just a little past halfway in the first paragraph. Everybody see where that is, okay? Either everybody sees it or you're ignoring me or I've put you to sleep and I get a yes. I'll take a yes. Okay. So that's the homogeneity. That's the is it too far out of whack to adjust for question. Then it goes on to say the Ancova was significant. So I'm scrolling down to the test of between subject effects to these two lines. This is the second part. And I would not, to me it would make more sense If you actually started a new paragraph with this, kind of like that 3-paragraph model we had before, so they don't do it here, but it would not morally offend me if you did. And it would seem to be to break it up a little more. So the Ancova was significant, and the description of that is F of 2 and 26 degrees of freedom respectively. There's the 2, there's the 26. That F value is 6.45. Comes again, the last value in the F column, because that's the F value. The mean square is 12.32. 12.317 in the output. Sometimes these roundings make it hard for me to match the numbers up sometimes. But that's the 12.32 they refer to in the paragraph. And P is less than 0.01 comes from right here. And I would say P is less than, I would say P is equal to 0.05, 005. Yeah, I would prefer. I like the p-value going out to 3 places because I think you could because that's the key number, and 3 places lets you be more accurate than 2 places. Yeah, if I were writing it, I would write it this way. Oops, no, I wouldn't. So yeah, I would probably just take P out to all 3 decimal places that he gives us. And then it tells us that the last thing, the strength of a relationship again between the independent and dependent variables, that's strong, assessed by at a square value, and they round that to 0.332, which they interpret as 33%. Again, that tells us the percentage of variance in one place is associated by the other place. So that gets me through the whole first paragraph. Even I probably would break that into 2, or at least I'd think about it. And then the next paragraph is when you actually can look at the individual things together or compared with each other. And that's where we made these comparisons. Placebo and low, placebo and high, and low and high. And we said that, oops, why can't I get that off of there? Try it again, Don. Oops. Yes, yes, and no. I have to give it 3 yeses. So, reading the last paragraph, the means of number of days of cold symptoms adjusted for initial difference were ordered across the 3 groups. The placebo group had the largest adjusted mean, and I can't show you that. I have to scroll back in a minute. M is equal to 12.01. Since we just saw that, let's go ahead and do that. Oh. And these are the adjusted means. Does it say adjusted anywhere? Estimated marginal means. These numbers right here, because they have adjusted them for initial differences. It does say adjusted in the paragraph. The placebo group had the largest adjusted mean, 12 point, right here, 198. They round that to 12.01. I don't know why they don't round that to 12 point, should be 12.2 actually. And then, hang on, I'm about to tell you something wrong here. There it is. Look at the wrong box. Okay. Vitamin C treatments under estimate, 12 point. 0.01 for the placebo, and then the smallest one was 7.71 for the low dose, and the high dose had was at 6.67. So they say, ended up saying based on these tests follow-up tests were conducted to evaluate pairwise differences among the adjusted mean based on the LSD procedure. I didn't know the LSD is one of those follow-up tests that this particular one defaults to. It means least squares difference, not what you're trying to think. The adjusted means for both vitamin C groups differed significantly from the placebo, and that's exactly what we said the first time we looked at the pairwise data. But the adjusted means between the two vitamin C groups, meaning the low and the high dose, did not differ significantly. So bottom line, plain English, if you took some vitamin C, there was a difference than if you didn't take some vitamin C. Didn't make much of a difference whether you took a lot or a little bit, though. Which is, again, consistent with the data we had the first time we analyzed this without running the covariant stuff first. Okay, thus end of the first example. Questions, comments, thoughts about that, and how that translates into a write-up. Everyone equally unhappy?